I am now recording this lesson, and we can see all of these answers that students have given to the question, what is a function? Uh, a function is a set of numbers. One set has a relation to another set of numbers. A relation from a set of inputs to a set of possible outputs. A relation of sets of an output where each input is exactly one output. You can see all these wonderful answers to this question. I'm moving on now, and we're going to have a mini lesson. In this mini lesson, I'm going to introduce a whole bunch of concepts. So I'm going to hit you with a whole bunch of vocabulary. And for those of you who want to review this vocabulary, who want to see the glossary for the course, I'm going to show you how you can access that content. Um, if you go to the class Google Drive page, uh, you will see this, which I need for notes, but I'm going to remember where it is uh, right here. And if you go to the class Google Drive page, you'll get to this directory right here. When you go to Clever and go to Google Drive, it'll take you here. If you go inside course materials, you'll see this resource here, definitions and properties. And starting on page 12 of this document, whoops, not there. Where is it? Not open. I guess I'll open it. If you look inside, yes, you can't see what I'm showing you. I'm sorry. How do I make it so you can see that? Let me stop this share and hit this share. Share screen 2. Share. So if you are in the class Google Drive page, there's a course materials directory that inside course materials is the definitions and properties file. This is kind of a glossary of the terms for the entire year. Inside here, the first thing is a history of mathematics, and that's a bunch of slides long with a ton of interesting content that hopefully we'll get to cover at some point soon. A list of the fields that make up mathematics, and some things about how you talk about truth and how you do modeling, how you model the real world with mathematics. Starting on page 11, you'll see there's a list of the kind of key sets that we're going to use in the class. Some of these will be pretty new to you, I imagine, complex numbers and pure imaginary numbers. We'll get to those later in this new unit. But then the terms I'm defining today, relation, function, domain, range, surjective, injective, bijective. There's some pictures to go with it. These terms here, really useful and really careful and precise definitions of those terms. Okay. The other thing I wanted to show you, you have 9 new Khan Academy exercises. I heard one student came in today. I'm not going to reveal her name unless she wants to reveal it. I heard one student come in and say that she got the notice during her break and was able to finish 6 of them already. I'm hoping that these exercises will be very useful to you and also a review. Okay, I'm going to stop sharing and go back and do this mini lesson now. So we're back, hopefully, to my notepad. Where we can talk about the first concept that I want to define, set, and I don't like to use green for just writing. The idea of a set is a pretty big idea that uh, we won't define precisely. Very analogous to a point, line, and plane in geometry. If you remember at the beginning of a geometry course, depending on the teacher you had, they might have made a bigger or less big deal about this. But at the beginning of a geometry course, the point, line, and the plane, those three concepts are really central to all the work you do in geometry. And at the high school level, it's very difficult to define those ideas with any sort of precision. Same thing is true with set. In college, if you take a math class called algebra, same name, but very different content from the content that we're doing here in Algebra 1 and Algebra 2 in high school. A college level algebra class, it does all of the content in Algebra 1 and Algebra 2, and some more, quite a bit more, but with a level of precision and detail that we just can't even approach. And one of the key concepts that takes up a month of time in a college algebra class is understanding what a set is and how a set works. So we're just going to give it this definition for our purposes, which is adequate but a little unsatisfying. It's a collection of elements. And I'm not really going to be able to define what I mean by collection or elements. I'm just going to give you a lot of examples that hopefully over time will start to feel like it makes sense. Okay, so and the first one we're going to do is a relation. A relation is a particular kind of set. Uh, it is a set consisting of correspondences uh, between two other sets, the domain and range. And I apologize for my handwriting. If my handwriting makes it tough to read, I'm doing my best, but I'm still learning how to have good readable handwriting through the iPad. So just shout out if you miss anything and you want me to reread anything or rewrite anything. But that's what we're going to use as a relation, and to understand it, let's start with some examples. Um, the first example, really the purpose of this example is to illustrate how general this idea is. I have a hard time making this symbol. Uh, it's what's called a brace, a left brace. There you go. It's the symbol that on your keyboard, if you look at the enter or return button on your keyboard, if you look above it to the left a little bit, that's called a brace. And it indicates that what's between the braces is a set, and it's a list of elements. And the first element in our relation is going to be uh, a relation that connects one element of our domain. Let's see how well I can draw this. Make it a little bigger so I can get an advantage. This is a little misshapen, but as good as I can do. What's that? No one's gonna. Oh no, look at his nose. Look at its nose. Yes, thank you. I gotta make the nose a little bigger. Somebody said a cat. My photorealistic drawing isn't like very clearly a pig. Anyways, uh, that's the relation is composed of our our pig mapping to $22. And actually, just to give you a sense of what this word correspondences mean, it's mapping. Like it maps one thing to another, right? In this relation here, we're mapping pig to $22. And then we're going to map also 527 to give me something else. Anything. It could be anything. Horse. Oh, no. Let's see if we could do a horse. That's the main. That's the eyes. It's much more dog-like than horse-like. Thank you. Positive encouragement. It helps. Yeah, what makes it a horse as opposed to a dog? I'm not sure. That's something to study. One of you is probably is an artist and can tell me. Say, oh yeah, their ears. It's all about the ears. That's not too bad. Anyways, we've got our mapping from pig to $22 and from 527, the number 527, to a horse. Uh, right? So, uh, doing examples, let's do another example of a relation. This one is going to be a little more typical, the kind of thing you more frequently encounter. One mapping to two, three mapping to five, and five mapping to two. Oh, this is not what I wanted everybody to see. So in the video, it's going to be very confusing because I had my notes up on the screen instead of my what I wanted. And I can't see the chat. There's the chat. Okay. Better handwriting than mine on real paper. Okay. Uh, so, and I can see my notes and the chat all at the same time. Folks, I can't imagine how frustrating it must be to have to deal with me learning all this technology with all your teachers, I'm sure, making sense of all their technology. Yes. Well, here we go. So we're going to look at this. I hear somebody saying, I hate domain and range. I was never able to get that. Well, here we go. So this relation right here, this relation here, if we look at one, we think of that as an element of the domain, right? What that means, that's kind of fancy language, but what that means is that it's in the box, right? Remember what domain is. Domain, well, we haven't actually defined it. We will define it later, but I'll just give you the preview. Domain is a set of elements, uh, and it can be a whole bunch of different things. Just like here we had the pig in our domain. So here, the pig in the domain mapped to 22 in the range, and 527 in the domain mapped to horse in the range. And here we have 1 mapping to 2 in the range, right? So 1 from the domain maps to 2 in the range. And if we draw out a picture showing the domain and the range, 1 is going to be an element in that box, in that domain box. Another element is 3, and a final element is 5. So we have those 3 elements corresponding to the first part of each of these mappings, right? 1 maps to 2, 3 maps to 5, and 5 maps to 2. So there's our domain. I'm going to draw on here the range, which is just 2 and 5. And what I'm drawing now, the thing I'm drawing now, is the relation. The relation isn't the domain. It isn't the range. It's the mapping from the domain to the range. So 1 maps to 2. That yellow arrow, that's part of the relation. That's this right here, right? And then we have the 3, 5. 3 maps to 5. That arrow is also in the relation. That's this right here. And finally, this 5 maps to 2. So the combination of those 3 arrows makes up our relation. The relation is the 3 arrows. Sorry, horrible handwriting. Okay. You're going to have some Khan Academy exercises that'll help get at this and help practice this. And I think each of these concepts, they'll build on the previous one, and it'll help force it to make a little more sense. Let's do function next. Function is a relation with the rule that there's only one y for each x. There we go. That's exactly where I'm going. Somebody just asked, the one on the right here, this relation here, this relation here, is it a function? Well, let's write the definition down and then analyze it together. A relation with the rule that there is only that every element in the domain maps to exactly one element in the range. So now we're going to do an analysis on both of these, and let's start with the first one first and see, is it a function? So this here, pig, maps to $22. Does pig map to anything other than $22? No. 527 maps to horse. Does 527 map to anything other than horse? No. Are there any other elements in the domain? No, the only elements in the domain is the pig and the 527. So each element in the domain, the pig and the 527, map to one and only one element in the range, so it is a function. And let's look at the next one. Here we see 1, an element in the domain. And what does it map to? 2, an element in the range. Does 1, the element in the domain, map to exactly one element in the range? Does that 1 map to anything other than 2? No, it maps to exactly one element in the range, just the 2. Okay, so the 1 is okay. What about 3? That's also in the domain. 3 maps to 5 in the range. 3 maps to 5. Does it map to anything other than 5? No. So that's okay as well. 5 in the domain maps to 2 in the range. Does it map to anything else other than 2? No. So 5 is okay as well. Every element in the domain maps to one and only one element in the range. It is a function. So the y can be different, but the x can't be different. Exactly. I like that way of putting it. And I always find that this definition is a little tricky to remember. It's like, which way does it work? We're going to have another definition in just a moment that will help clarify. So both of the kind of cases are dealt with, and we're going to try to make sense of those. But before we do, before we get the new word, let's let's try and think about this question in a graphical context. So what does this look like in a graphical context? Uh, well, and how can I tell if an element is a function by looking at its graph? Anyone have any ideas? How can you tell? Thinking about what we just did, the work we just did, the way that we just looked carefully at the definition and used our definition on a couple of examples and determined that both of those examples satisfy the requirement in the definition. I want you to think, can you kind of translate this definition to the geometry context? We've got an algebraic definition. I want to see, can you think about what this looks like in geometry? How could I tell if a relation is a function by looking at its graph? Oops, wrong color. Anyone have any thoughts? How can you tell for a graph whether it is a function or not? If it's linear, you know that it is a function. I like that. Uh, What if you have a bunch of points all over the graph? What if we had a graph of this? What if I graphed those points there? Yes. No, I didn't. So I heard you say if it's it's a function if the graph is linear and the slope makes the equation true. Uh, the response that I had to that uh, was to look at this, or the question that I asked to that is to take this that we just looked at, and based on the definition, we decided this thing in the kind of weird red shoe that that is a function. And I wanted to plot those points on a graph and see if those points, how those points match up with your idea about the linear thing, and also just how they what we could do with that graph to figure out if it is a function. We already know the answer, it is a function, so we're just thinking why, basically. So if I go to 3, 1, 2, 3, that first point was 1, 2, 3, 3, 4, 5. Okay, so I've got 1, 2, 3, 5, and now 3, 4, 5, 2. So I've got those 3 points. What would be true if this wasn't a function? What would I need to do? And this gives us a chance to actually, let's take this here and let's modify it so that it's no longer a function. Let's write an alternative version of it that's not a function. Yeah, go. Say it again. Oh, also I noticed that I made a mistake on my graph. I put this point that I was supposed to graph here. Well, I put it 1, 3, but it was supposed to be at 1, 2. So there's 1, 2, and there's 5, 2. So that's a better picture uh, of the graph, better plot. Can you throw out there what you said one more time? Is not a function, a horizontal line. Interesting. Let's. I'm going to take a step back. I think I moved past this too fast. Let's forget about the graph for a minute. Just eliminate that from your mind for a minute. And I want you to look at this, and I want you to tell me, how can you modify that so that it is not a function? We decided that was a function. I want you to modify it, make another relation that is not a function. Exactly. The For it to not be a function, the range has to have more than one value for a given x value, a given input value, a given value from the domain. So how could we do that? If I put this here, can you give me another point that would make it so that the relation is not a function? 5 comma 3. So now we see that, oh, you meant, I might have been confused about what you meant. Is this relation now a function? It is still a function. So you're proposing keeping these here and adding 5 comma 3 to it, I think. Now, is that relation a function? What do people think? Is that relation, this relation right here, is that a function? Well, let's test it out. 1, what does it map to? 2, does 1 map to anything other than 2? Not 1, not 1, not 1, no. So that's okay. 5 maps to 3. Does 5 map to anything other than 3? Yes, it also maps to 2. 5 maps to both 3 and 2, so not a function. Okay. I didn't leave enough. I took up all my space where I was hoping to put a graph of this. So I'm going to do this. Move it underneath and then do this. There we go. And actually just erase it back up here. There we go. Okay. So now we took this example here. Whoa, we took this example here and we modified it to make this example, which is not a function. Let's look at the graph of this new thing. So we've got 1, 2. Let's plot these points. 1, 2, 5, 3, 3, 5, and 5, 2. How can I tell just from looking at that graph? How can I tell? Let me zoom in. How can I tell just from looking at that graph that those 4 points are not a function? What's happening with those points that make it not a function? What line? So if I draw a line, what kind of line? A vertical line. Oh, if I draw this vertical line, what happens one more time to that vertical line? Okay. I shouldn't use yellow or orange or whatever. It's pretty tough to read. The vertical line goes through 2 points. So not a function. And does that remind everyone of what graphical test we can use to determine if something's a function? What am I doing with this vertical line here? You got it. It's called the vertical line test, and you might not have heard it before. The vertical line test is a tool for testing to see if a relation is a function. For something to not be a function, it doesn't matter what the range is, it matters the domains are the same. Yeah. Uh, if you have, right, remember, uh, for it to be a function, every element in the domain has to map to exactly one element in the range, right? And here, these 2 points here, we have one element in the domain, 5, mapping to two different elements in the range, 2 and 3. So that's violating that rule from our definition for the function. Okay, and the way we're going to define the vertical line test, or the way we're going to write the vertical line test, oh, fiddlesticks. There are no desktop screens. I just lost my uh, notes, which is super confusing. Why would it do that? I was having such a good time. Ugh. Now I don't have my notes. Well, we'll do this from no, because, oh, there we go. It's back. Hopefully. I think so. Okay, my notes are back. Which is important because that's also our Nearpod, which we need to get to pretty soon. Vertical line test says consider all vertical lines. And sometimes this is a lot to consider. Sometimes it's infinitely many vertical lines. All vertical lines uh, drawn at every point in the relation. Or I guess we don't need the word all here. Every uh, value in the domain. If any vertical line intersects 2 points of the relation, uh, it is not a function. Okay. We need to talk about function notation and how function notation works. And I think we're going to have to, I promised you something about one-to-one functions. I think we're going to have to save that for next time because I want to get you to do some practice problems here. So let's finish this up with function notation. So what's the whole point of having functions? Why have functions and not just y equals 3x plus 5? Why use this whole idea of functions? Well, it allows you then, when you have multiple different equations, um, it allows you to name those different equations and operate on them individually. Uh, so the notation is f of x is the uh, value in the range corresponding to x in the domain. So if we go back up to our examples up here, we can see that this 2 right here, right, this was a function. This 2 is the output when 1 is the input. So we would call that, or could call that, f of 2, assuming this is f, assuming we've defined this or named that relationship as f. Then f of 2 would, it's sorry, whoa, I can't believe I said f of 2. F of 1 would be 2. And this 5 here, that's f of 3. And this 2 here is f of 5. So I'm able to refer to the output, f of 5 is equal to 2. I'm able to refer to the output of the function f when the input is 5. So if the input is 5, I get an output of 2. And it captures that mapping, that notation. Okay, let's go to some examples here. Enough from these notes. I'm going to stop sharing and we're going to transition to Nearpod for the last few minutes of class, last 20 minutes of class. And I am going to record this. I think it'll be helpful. The first question I want to ask, can ice cream flavor be represented as a function of the type of shoe? Weird question, right? Weird question, but trying to push you to accept the generality of relations and functions. Doesn't have to be number mapping to number. It can be all sorts of things mapping to any other sort of thing. So here we have a relation. We have boots mapping to strawberry, loafers mapping to vanilla, sandals to chocolate. And we're asking, is this set of mappings, having the shoes mapped to the ice cream flavors, is that a function? Can you make a function like that? It means that uh, it's the arrows. It was those orange arrows that I drew. So the question I got was, what does mapping mean? Mapping is like a connection. It's like we had the pig mapped to $22. That was a mapping from the pig to $22, and that relation also mapped 572 to, or 527 to a horse, right? That was the mapping. And I hear some people shouting answers on this. Wouldn't that be a no? And I see a lot of yeses and nos, and I can't tell which one is which. I don't know if A is yes or B is no. Uh, but looking at, and I'm going to share so you can all see now. Yes, no. The question I got was, does range have to be an amount or number? It does not. Uh, can anyone tell me, can it be a function? And if not, why not? Oh, maps to vanilla. Maps to vanilla. Okay, so that looks fine. Wait, what about chocolate? I'm going to encourage you. I hear some people saying it is a function, right? Loafers works. It's kind of a trick because loafers shows up twice in the domain. Oh, but it actually maps to the same thing. So it really only shows up once. Loafers only maps to vanilla. Yep, that is true. Uh, but I want you to look carefully. You might have to look at Zoom if you've already submitted. I want you to look carefully. Uh, is this actually a function? There's something else you have to look at. Sandals. What happens with sandals? Maps to chocolate. Okay, that's fine. But oh, down here, sandals also maps to banana. Right? That can't happen. So it is not a function. Okay, that was fun. Another one. Here we go. Do this on your own. Does the graph represent a function? And if not, why not? Well, all you can answer is the yes, no. But think about why not. Or think about why it does, if it does. Anyone? Yes. Okay, sounds good. You're leaving to go to an appointment, and at the same time as you were saying that, I heard a student saying it is not a function because -3 here and -6 share the same domain. What domain value? 3. And can anyone describe that using a graphical test? Yes. What vertical line do I draw? Yeah, if I draw this vertical line, I picked a bad color for this. That aqua color goes through 2 points, right? If I draw the vertical line through the point 3, -6, it also goes through the point 3, -3. So not a function. Excellent. And here we go. If you click this, it makes it bigger. F of x equals 5x minus 3. What's f of 5? And we have our student back. Excellent. Uh, and I should look to see. We have lots of answers in. We have lots of 22s. Can someone explain 22? How are you getting 22? What are you doing to get 22? 5 times 5 is 25 minus 3 is 22. Thank you very much. You plug the 5 in for the x. Okay, next problem. Please mark any relative maxima on the graph. And I am going to take a big risk here that might mess everything up. I sure hope it doesn't. We'll see. Okay. That's sure confusing. I minimized it though. Doesn't mean it's not running. And now I go to Duet and I say disconnect, which seems to always cause a problem, but it worked this time. Computer, it's working for me. Duet. And I go to iOS. I'm on iOS. I hit air here. I go to air here. And I'm going to simply mirror what's going on so I don't get myself completely confused. And I have it. There we go. And we have a submission here. We are trying to find relative maxima. Maxima, M-A-X, I don't even know how to spell it. Maxima is just a fancy way of saying maximums with an S at the end. So relative maxima. And this student, you can see, marked this as a relative maxima, and that student is completely correct, and that is the only relative maxima on this graph. I saw a number of other students mark points like this one down here as relative maximum. Let's use this as a chance to define what we mean by relative maximum. We didn't get to it in the definition section. So a relative maximum is a value, a point where there is an interval. And we're going to think of this interval as left bound, right bound. Just like when we were doing graphs, remember when we were doing left bound, right bound in graphs? What you were doing when you were doing that was creating an interval as well. And a relative maximum is a point that is in an open interval and is the highest point in the open interval. So what does an open interval mean? Well, an open interval is an interval where you don't have the less than equals, when you don't have the equals bars on the less than. So here we have -1 less than x less than 1. That's our interval from -1 to 1. And in that interval, is there a highest point? And yes, that's the highest point. So that is a relative maximum. Now, what if we considered this point over here? There is an interval that contains that point, right? With our left bound and our right bound. But in that interval, this point is not the highest point. What is the highest point? Well, isn't it this point right here? Isn't that the highest point in that interval? That green point? Kind of. Remember, this is an open interval. That point that's at 4, -4, right? This point at 4, -4 isn't included. 4 isn't included, right? We're going from 4 less than x less than 6. 4 is not included. So if we take that point out, if we leave that point out, is there still a highest point in that interval? Well, we could think about the point that's a teeny bit to the right of that point. Maybe that's the highest point. No, there should be another one that's even closer to the green point, but higher. Maybe that's the highest point. No, there's another point that's even closer to the green point, but higher. Would you ever get to a highest point now that you've taken out the green point? No, there's always going to be something that's a little closer to the green point. There's no end to that process. So there is no relative maximum here. The only relative maximum is right up here. There's no relative maximum in this interval right here. Okay, next problem. Any questions on that? Mark the absolute maximum now. I want everyone to mark the absolute maximum. And we see right away somebody correctly marks this point right here as the absolute maximum. It is an absolute maximum. You're correct. Let's complicate things. Is that point also a relative maximum? This point right here, the absolute maximum, is it also a relative maximum? Can you make a open interval on the domain? So the domain goes from -6 to 7. It includes -6 and 7, but when you're making an open interval, you can't include those values. Can you make an open interval that contains that point? And the answer actually is no. This point corresponds to an x value of 7. It's 7, 7. And your open interval can't contain 7. So that point is not a relative maximum. It is the absolute maximum, yes, but it is not a relative maximum. There are a bunch of relative maxima, though. There's a relative maxima. There's another relative maxima, another one, and another one. So we have 4 relative maxima and 1 absolute maximum. What about absolute minimum? Is there an absolute minimum? Yes, the lowest one. But if you'll notice, those two are both the same y value, -5.5. So there's two, well, those are relative minima because they are contained in open intervals like that. These are also relative minima. So you have 1, 2, 3, 4, 5 relative minima, but these are both relative maximas, relative absolute maximum, absolute minimums. Say it again. Yes, that makes them absolute minimums. They are the lowest points in the whole graph. So they are absolute minimas. They're also relative minimas. So it's possible to have an absolute minimum that is also a relative minimum. The important thing for relative minimums is that there's an interval that's an open interval that contains the point. And we can make this open interval where that's the left bound and that's the right bound. That's the left bound and that's the right bound. And this point is contained between those left bound, right bound in that interval. Okay, just enough time for this last piece as an exit ticket. Should I do it? Maybe not. Let's see. Okay, start activity. 3 minutes. Do it. Let's go. Yeah, understood. You're not going to be able to do this Nearpod probably in the car. I'll put the link in the chat just so you can see it, and it'll still be up afterwards, so you'll be able to study it later. And I am going to stop recording so I don't accidentally. Uh, well, this isn't a lot of tabs. This is actually the recording software that I'm going to hit